My name is Antoine Coad. I'm Senior Developer Relations Engineer at Intel, working with game developers to help them optimize their games for Intel hardware. And I'm here today with Mike Apodaca, who is Principal Engineer in charge of our driver. And we wanted to talk to you guys today about Gen11, which is our latest generation integrated graphics platform. So today, the quick agenda, we're going to go over brief overview of the graphics pipeline, of how it works and how it matches to Gen11 graphics. And then we're going to go dive into details into every single of the hardware blocks. And for each hardware block, we're going to see how it works, and then we're going to give you some performance tips. One thing that's important for you to know is that, well, Gen11 is an incremental improvement over Gen 9. So actually, a lot of the performance tips I'm going to give you today are also applying to Gen 9. And basically, that means that if you optimize for that platform, you're going to see a lot of benefits on the millions of platforms that we are already sold over the past few years. And once that's done, I'll hand it over to Mike, who is going to cover some of the pretty cool new features that we've been adding to Gen 11, like the tile-based rendering and the coarse pixel shading. So this is the graphics pipeline from 10,000 meters level. So for you American, 10,000 meters is approximately 35,000 feet. So basically, when you submit a draw from the application level, it goes through the API layer, the driver layer, and then submit it to the GPU. And the first GPU block that reads it is the command streamer. What the command streamer does is that it takes that command and passes it along to either the geometry fix function, if it's a draw command, or I'll cover later what it does in case of a compute command. Then the geometry fix function just is going to fetch all of the primitives and is going to submit them to the compute block so that it does all the primitive transformation, and then passes it along to the rasterizer, which basically transforms all of the primitives into pixels. We also have been adding, for efficiency purpose, depth test block there. And then once you've been rasterizing your pixels, you can shade the final color in the compute block. That's going to get some sampler data from the memory and writing the output into the pixel backend. So fairly straightforward. In case of compute command, well, the command streamer just takes the command and go through the thread dispatcher that's dispatching it to the compute blocks, which is going to do whatever particle simulation you want it to do, and then write the output into memory. Now, how does that match to Gen? Well, so this is a block diagram of what Gen looked like. And at the very top level here, oh, let's turn it down, it works better. Here you have a block called the unslice. And on the unslice, you have the two first blocks that I mentioned, which are the command streamer and the geometry fix function. To be more accurate, the command streamer is part of a bigger blocks called the global assets that handles every single communication with what external to the GPU. So it does have stuff such as the ring buffer, the power management, a blitter, the thread dispatch, etc. Then you have the geometric fix function I already talked about. And there's also low power encode and decode hardware block. I'm not going to cover it today because we're going to focus on the graphics part of it. If you have any questions, don't hesitate, come and talk to us at the end, and we can go into details together. So the top block, the unslice. The rest of the GPU, all this is called the slice. And you have in the middle what we call the slice common. The slice common has the block that I mentioned earlier, so the rasterizer, the depth path, the pixel backend, as well as the L3 cache marked as memory here. And the rest of the slice is called actually 8 subslices, and each subslices is an array of execution units, which are our graphics core. It has instruction caches, texture samplers, and load and store units, etc. Now, let's dive into every single one of these blocks separately. First, the unslice. So as I mentioned, you have the media fix function, the global assets, with the command streamer inside. The command streamer is a fairly straightforward block. So what it does is that it just reads from a ring buffer the commands, parses them, and then dispatches them, either to the geometry fix function block in case of 3D commands, either to a thread dispatcher, which is going to dispatch them to the execution unit in case of a dispatch. One thing that is important to notice is that the command streamer is also in charge of building complex commands such as the draw indirects. And that can become a problem because by design, the command streamer doesn't need a lot of performance as it just passes the command along. However, if the command is complex to build in case of draw indirects, it might take some time to build the command and it might starve the rest of the pipeline. You can see the command streamer, like your manager, is just not really fast and not really smart. It just passes the command along. But if it's a complex order that it needs to give, then you might end up being stopped from work. So here, the performance tips is really avoid a lot of small empty draw indirects when case you're doing GPU-driven rendering type of approach. And if you do, use either D3D12 execute indirect or the multi-draw indirect extension that not all of the AHV support. Another thing that is important to know about Gen graphics is that when switching from 3D to compute, it requires some reconfiguration, which means that basically, if you have a lot of 3D to compute switches, you're going to end up reconfiguring a lot and wasting a lot of compute time. So we suggest that you separate and regroup you regroup 3D commands together and compute commands together to get the most of the hardware. So moving to the commands, so the command now goes to the geometry fix function. At the very high level, what it does is that it fetches the data from memory. Remember, like as with draw index, the vertices are probably not contiguous in memory. It is going to dispatch threads to the compute unit to do the vertex shading part of the work. And then it's guaranteeing that all of the output is written in order into memory. The geometry fix function has been increasing quite a lot over Gen 9, so we're now capable of fetching 6 vertices per clock instead of 4, and up to 3 primitives per clock. So we are pretty excited about the fact that it goes much faster, but it can still become a really big bottleneck, especially on geometry intense passes such as shadow maps or depth prepass. So there's a bunch of advice that you can do to help the geometry fix function here. First of all, it's trying to pack your attributes into float 4. As you noticed, the fix function is fetching attributes one by one, and having them packed into like a smaller amount of float 4 will help in the performance there. And the other stuff you can do is try to avoid submitting primitives that are not contributing to the final scene, right? So you really need to pay attention to CPU occlusion calling, size calling, implementing good level of details, frustum calling, backface calling, and work with your artists on that kind of stuff. Basically, we ask you to really call all the triangles. So now that we have primitives that are transformed, we can pass them on to the rasterizer. And the rasterizer does, it's actually working all through all of the triangles and detect which pixels are inside or outside. It's actually doing quite a lot more stuff. So it handles the clipping, it does the viewport scaling, it does some orientation and thin triangles calling. It's computing the equation edges for the triangles, the edges equation for the triangles, and of course, it does the rasterization. The way rasterization is done on Gen, it's hierarchical, which basically means that we are going to work through blocks of 256 pixels, so 16 by 16, and determines if each of these blocks is fully covered, partially covered, or void. Then for all the blocks that are partially covered, we're going to work each 4x4 block, compare the four corners against the edges equation, and we're going to determine if each of these span is fully covered, partially covered, or void. And finally, for all the ones that are partially covered, we will do fine-grained rasterization at 16 pixels per clock. As you understood, the rasterizer is capable of processing a lot of pixels per clock. However, it is still limited to one triangle per clock. So having really, really small triangles, like the case here on the right, you're going to have a really low efficiency because in 3 cycles, you're actually going to rasterize only 3 pixels, sorry. However, if you have cases with bigger triangles, such as the one on the left here, you can rasterize up to 15 pixels per clock. So as a performance tips, really pay attention to the ratio primitive to pixels you have, and you can improve that by using level of details, using imposters, doing stuff like size calling, I already mentioned in the previous slide, and try to increase the ratio pixel to primitives. So now that we have pixels, we can shade them, right, and pass them to the execution unit. Well, not quite. Now that we actually know where the pixel is on screen, we can actually know if it's going to actually contribute to the final image or not. And we can do that. We can just delete all of the pixels that are hidden. And this is done by the early depth pipe. And again, it's done in a hierarchical manner. So it's capable of handling each pipe is capable of handling 64 pixels per clock, and it has 2 modes. Basically, the ideal mode is when you have only one triangle covering each span. And in that case, what we do is that we only store the plane equation, and we can easily detect if the new upcoming triangle is in front or behind that plane. If there is another triangle that intersects on that span, we need to change mode, and we go to min and max mode, where we actually store the minimum depth value and the maximum depth value for that 4x4 block. And then we can easily identify if the pixel depth value is higher than the max, it's trivially rejected. If it's lower than the mean, it's trivially accepted. However, if it goes between min and max value, then we need to go to intermediate Z mode, which is doing fine-grain calling and is doing it per pixel. Performance-wise, the hierarchical Z test has 2 pipes, and each pipe is capable of 64 pixels per clock, and each pipe has a 12 kilobyte cache. And the intermediate Z test is capable of handling 16 pixels per clock, and each pipe has 32 kilobytes of cache. So as I mentioned earlier, we can do early depth testing, but this requires one major condition for doing this, and that condition is that we do not need the pixel shader to know the final depth value. And there's 2 cases mostly when that's not the case. The first one is when you call a discard in the pixel shader. In this case, we do not know if the pixel is going to be written out or not. So we can test if it's hidden before the pixel shader, but we cannot write the output value. The second case where we do not know is when you write depths manually in a pixel shader. And in this case, both the depth test and the depth write is going to need to happen after pixel shader processing in the pixel backend. So now that we have pixels and we've gotten rid of as much as possible hidden pixels, we can start doing the pixel shading. And this is done in our compute blocks which are called the execution units. Gen11 has 64 execution units. So execution units are here to execute math, right? And so let's dive into how we're doing math. Each execution unit has two SIMD4 ALU block. Each ALU supports a floating point and integer math and is capable of one instruction per clock. We're also capable of doing math half precision at double throughput. So that means that with the two ALUs, one execution unit is capable of 8 32-bit or 16 16-bit operations per cycle. One of the ALU is capable of high throughput transcendental math. What we mean by high throughput is that it's actually half the speed of the basic instructions that are the multiply, the add, the add, etc. However, as it's only one of the ALU, that means that all of the transcendental math operations are actually going to happen at quarter rate. So stuff like square root, trigonometrical operations, etc. The minimum latency for the operations is 2 cycles. However, they're fully pipelined, so we are capable of starting one instruction per clock and instruction complete every cycle. Now that we know how we compute in the GNLU, where do these instructions come from? Well, they do come from the 7 threads that we have in each execution unit. So why do execution units have threads? Well, GPUs are big, so memory, when you do memory operations, it takes some time to come along. So essentially, we have threads so that rather than stalling and waiting for the data, we can trigger some more operations. And why 7? Well, this was determined by our architects. They studied a lot of workload, and they established that 7 was the value to which we had the best efficiency for this. Each thread can run shader it can be one different thread per shader, and each of these threads requires memory to store the data, right? So they have dedicated register space. Each of them has 4 kilobytes of it, and each register is 8 times 32-bit. So it's one 32-bit value per SIMD lane we have in the hardware. I'll spare you the math. That actually means that we have 128 registers or GRF per execution unit. I'll ask you to remember that number because we're going to need it for later. And now, how are the thread instructions dispatched to the ALUs? Well, it's done in the thread control block. And basically, the thread control or thread arbiter just picks instructions from runnable thread and dispatches them to one of the 4 functional units we have on Gen. The 4 functional units we have, 2 of them I already mentioned are the ALUs, and the 2 other are the send instruction that's in charge of every memory operation with outside of the ALU, and the branch instruction for the branch unit for branching. And the thread arbiter can co-issue up to 4 instructions per clock, so 1 for each of the functional units. Now, let me go into more detail about how our SIMDness works. So, as this is really particular to Gen. So, natively, as I mentioned, we are SIMD 4x2 or SIMD 8, but we do logically support variable SIMDness. And basically, the reasons why we do that is that if we run in SIMD 16 or SIMD 32, we are going to be able to have even more latency hiding capabilities and better performance. You're going to ask me why not always running into SIMD 16 or SIMD 32. Well, the reasons behind it is that when we run in those higher SIMD modes, we need to pair adjacent GRF together in order to store the local data, right? So, for instance, if you want to run in SIMD 16, you would need to pair 2 GRF together into a single 64-byte GRF. And the problem with that is if you use all of this memory, you're going to need to spill into memory. And that is terribly inefficient. So we always try to pick up the best SIMDiness for which we don't spill. And on for graphics workload is the 3D compiler that makes the decision if we're running either in SIMD8 or SIMD16. So as you understood, we want to have the higher SIMDiness, and for that we want to reduce the register pressure. First of all, yeah, for SIMDiness reason, and second of all, because it allows to reduce spills in case you're using all of it. It is also allowing much better code generation, simply because our compiler always does his best effort not to spill. So essentially, sometimes it's going to do some unnatural gymnastics to try to fit into all this into this memory. I put a small summary table of what that means. As we have 128 GRF, if we're using less than half of them, so less than 64, we are going to be able to pair GRF together and be able to run in SIMD16. If we are using between 64 and 128, we will be running in SIMD8. And if we are using more than 128 GRF, not only we're going to run in SIMD8, but we're also going to spill. We do have GPA that shows some data that allows you to check that kind of things. And we, since yesterday, have a standalone compiler that you can integrate in your toolchain that will allow you to check the ISA and make sure that you run efficiently. So quite often when I talk about that to developers, they're like, yeah, that's really nice, reducing register pressure, but how do we actually do that? I'm not going to go too much into detail because we could talk for hours about it, but I just want to give a small, short summary of stuff that you should try to avoid or do. Number one is branch on constant buffer condition. So basically having an if loop and checking on your constant buffer value. That's terribly inefficient because the compiler doesn't know which branch you're going to be using, so it needs to generate more code than it should if you had generated different shader permutation. As a matter of fact, I was at a studio 3 weeks ago, and we did such an optimization, so removing that condition and creating 2 shaders instead that we choose on the CPU side, and that saved us like 25% performance for that particular shader. And the good thing is that it also helped on other platforms, and we saw 15% benefits on Xbox. Other things you should do is you shouldn't do non-uniform access data to buffer. Basically, that means that you would need to store one variable per lane rather than storing once for the whole thread. Excessive variable declarations, declaring arrays and using them indexing into your shader is usually not great, again, because we're trying to reduce the register used. Stuff you should do and try to do. Number one is really use of partial precision. I already mentioned on the previous slide, we actually do also support double throughput math, and you're going to use half of the register required. So that's really one thing you should consider for performance. And the last point that you should try to do is try to move the command code outside of the branches, again, to avoid to have to store into per lane registers. There's a lot more details into the Gen graphics performance guide, and that one is pointing to the Gen 9 version of it, but we will be releasing within the next few months an updated Gen 11 version with a lot more things you can do. So now that we know how the execution unit works, we actually, to compute the final color, we probably need sampler data, lighting data, etc. So how do we get it? Well, we get it through the sampler. And for efficiency purpose, we have been grouping execution units together into an array of 8 executions, together with one sampler to feed all of these execution units. That block here is called one subslice. The way the sampler works is that it takes requests from the EUs. It's going to compute the level of details. It's going to compute the addresses in memory. It is going to handle filtering and fetching the textiles and returning them to the execution units. There's other stuff that it does, such as handling text decompression for either for lossless, for lossy texture compression that you might have in your engine, or lossless compression, and we're going to talk about it a bit more in details later. The performance-wise, the sampler is capable of handling 4 texels per clock by linear or point sampling for everything smaller than 64-bit, and ISO 2x for 32-bit format. For all of the other formats, such as higher than 64, but I don't think anyone really uses 128-bit formats in games, and ISO 4x, we're running at half speed. The sampler has multiple of caches for state and textures. I won't go into detail into this talk. Stuff you can do in order to help with sampler performance if you detect that your sampler limited. Number one is really spatial locality. Try to, when you're doing texture fetches, fetch texels that are in the same space so that there's a high likelihood that they're going to be on the same cache line and you avoid cache trashing. Reducing texture state changes. So basically, texture state is a combination of texture format and sampling state. And basically, our sampler is only capable of sampling a certain amount of them at a time. So if you have too many permutations inside the same shader, you might end up stalling on texture state. And then it seems logical, but sometimes we're surprised to still see that. On mainstream hardware, try to use simpler filtering mode. As an example, if you're using anisotropic 16x, well, it's 16 times slower than bilinear filtering, and you probably should not be using it on mainstream hardware. Another particularity of the subslice is that when you dispatch compute shaders, they're guaranteed to run on the single subslice. And why is that a problem? Well, in case you're using really big thread groups, such as 1024, they might not fit into the subslice. So Gen hardware is capable of running, has 8 execution units per subslice, and each execution unit is capable of running 7 hardware threads. So that is 56 hardware threads per subslice. If we have a thread group of 1024, and if we run SIMD16, we'd have 64 threads to be hardware. We would require 64 hardware threads, which is bigger than the 56 we have available. And to compensate, the shader is forced to go in SIMD32 mode rather than SIMD16, which would be more efficient. And that causes 2 main issues. The number one is that the occupancy will be low because you would have only 32 hardware threads running out of the 56 available on the subslice, which is an occupancy of 57%. The number two is that you're going to run into spill-fill issues. Basically, running in SIMD32, you double the register usage that you would have in SIMD16, and you would potentially be spilling. So as a performance tip here, we recommend that you use 8x8 thread group. It's fairly friendly for all hardware manufacturers, and it helps us in this case. Now, there is one thing that's pretty new about Gen11 over Gen9, is that we have been moving the shared local memory from the main memory to the subslice. And basically, we've been grouping 2 subslices together with shared local memory. Shared local memory is 128 kilobyte, which is twice what, well, 4 times what the Microsoft specs allows. And it's capable of 128 byte per clock throughput. And as we moved it closer to the subslices, we now have the quarter of the latency of Gen 9. So that's pretty exciting. We're looking forward to see what you guys are going to be doing with the additional shared local memory. One thing that you need to be careful with shared local memory is that using too much can hurt the occupancy. Like for instance, if you are using 32 kilobyte, which is the maximum that the DX specs allows, well, there's not going to be enough to fill all of the EUs with thread groups of 32 kilobytes. So essentially, you're going to run into similar issues that I described with the bigger thread group. And as you access it manually, sometimes if you don't pay attention, you may be reading or writing to partial cache lines, and those partial cache writes and reads are pretty inefficient on Gen graphics. The other thing that we've been regrouping together with the shared local memory is the data port. The data port is in charge of every communication with the external part of the subslice of the GPU. So basically, it handles the communication with the L3 at 64 kilobytes per clock. And it does stuff like constant buffer reads. It just forwards the request from the sampler. And it does UAV read-writes. And this is quite important that it does UAV read-writes directly through the to the execution units, because as I mentioned earlier in the sampler part, it's the sampler that handles the decompression. So that means that if you're doing a UAV write, it cannot be decompressed by the data port, and which means that when you create a UAV for a resource, well, the driver is going to flag it as that resource cannot be decompressed because potentially it's going to be read by the data port and not by the sampler, and it cannot be decompressed, and that would be problematic. So really try to only create UAVs when you require them. So now that we have pixels and we've been computing the final color with the execution unit, getting some texture data, we can write it out, and that is done through the pixel backend. The pixel backend handles color writes and blending to render target. It handles also gamma correction and that kind of thing. Performance-wise, it does both writes and blend at 16 pixels per clock, which is double the throughput that one Gen9 has, and it has its own 32K color cache. It is also handling the lossless decompression that I mentioned about. So Pixel Backends compresses it, and it can be read either when writing the render target. Well, it says bandwidth when writing the render target data. It says bandwidth when it's being sent to the display engine to be displayed on screen. And it says bandwidth through when it's being read through the sampler. And as I mentioned, the sampler is going to decompress then and passes it along to the execution unit. One thing that is important to note is that MSA textures are not compressed. So as a small summary of what we've seen so far, we have, when you submit the commands to the GPU, it goes through the command streamer that passes it along to the fix function, then dispatches to the rasterizer, the depth test, then you compute the final color into the execution units using some of the sampler data, and then write it out using the pixel backend. So this is kind of how the hardware works, and now we've also been adding some pretty cool, neat features, and I'm going to hand it over to Mike, who is going to talk about it.
All right. Thank you. All right, so the first thing I want to talk about is tile-based rendering. So tile-based rendering obviously has been around for a long time. You guys have probably seen this before, but ultimately the problem that we're trying to solve here is a bandwidth problem and a power problem. And so in some of our form factors where we're trying to get to these really low TDPs, we need to have some sort of solution to come up and solve this. However, one of the things that we don't want to be dealing with is a lot of the disadvantages of being a tile-only hardware solution. So what we have is something that we call this PTBR. It's position-only shading, tile-based rendering. And so what we do here is on the left-hand side, this pipeline, we actually have a second geometry pipeline that is running ahead and calculating position only. So the driver is doing its magic and taking the vertex shaders from the application, recompiling them to only calculate position. We run it through the rasterizer as well to figure out what the end visible triangles are going to be. We have this unit down here called the OVR unit, it's Object Visibility Recorder. And what this guy is doing is basically outputting a highly compressed visibility token stream to memory. Then we take that and on a per tile basis, then we run it back through the traditional geometry pipeline. These guys are actually running concurrently, so they likely the position only part here is running ahead, doing as many draw calls as it can, or even onto future render passes as well. And so then we do all the traditional rerunning of the geometry, and there's some communication even with the traditional pipeline with the OVR unit to make sure that it's matching up for the particular token stream. Hey, is this the right primitive, and is it visible or not? And if it's not visible, then it'll just drop it on the floor and not run it through the full pipeline over there. And ultimately what this gives us on the driver side is the flexibility to only have to enable this where it actually matters. And particularly for tile-based rendering, that is in areas where you're really bandwidth limited, or you are doing a lot of blending and operations like that. So from a performance standpoint, a couple of tips here for developers. One is there are some API constructs like the Vulkan passes and subpasses, and in there's the metadata with regard to for a particular attachment, whether you need it after the pass and so forth. So those things, there's a lot of documentation on, but be sure to use those when you can, because the driver will definitely take advantage of that. And in D3D12, they very recently added render passes to that as well. That's also a key for the D3D12 driver to kick on and use this technology. If you don't use it in DX12, you're not going to get this at all. For older APIs, it's all just kind of driver magic under the hood. And again, there are some limitations for this tile-based rendering. We're not supporting, the D3D tessellation or geometry shading, and it also doesn't support compute shading. So if you're doing those things in the middle of those render passes, we will most likely disable the tile-based rendering again. So that means if you do have, you don't want to be using those and be bandwidth limited at the same time. Basically is the long story short. Another thing is that the position-only pipeline, is reading from the vertex data. And so if your attribute buffers, your vertex buffers only contain those elements, potentially only position, that are needed by the vertex shader to calculate the final pixel position, then you can actually save a lot of bandwidth on the front end as well. And then one last note, if you're using GPA, if you're ever using the per draw analysis, you might notice some differences with regard to some of the performance data, because in that case, the tile-based rendering will be disabled, and that's just for ease of use, both on the driver and for the user of that. But it still works if you're doing, full frame analysis. Okay, next big feature we have is the coarse pixel shading. So, the big motivation here, we've talked about this for a number of years, and what we're looking for here is you've got resolutions that are dramatically increasing up to potential of 4K, and but for mainstream GPUs, really keeping up and doing that much pixel processing is sometimes very difficult. And there's a lot of software solutions that we've developed that are actually on the Intel website, some samples and so forth for some of these things. But this is looking at actually a hardware solution that's been developed. So I think Microsoft announced this morning the variable rate shading. So this is the tier 1 support for variable rate shading coming up in the new DirectX 12 API. And so we essentially have the ability to now change the shading rate and only do full pixel rate shading, or what's called like a coarse rate shading, depending on the application can program this and say, for these particular draw calls, I want to do like a 4x4 coarse rate rather than the full detail one. And what's really nice about this is that it gives the application now control to know for the particular draw calls that are really important, that you want the highest detail, you have the full control over that. And a lot of the demos and samples that you'll see, it's really hard to actually tell the difference. And the last point we want to make here is actually our hardware goes beyond the tier 1. We have this foveated mode as well. And what that is you can specify these elliptical regions, and the hardware will actually take care of picking the right course rate depending on where you are in those regions. So if that is something that you're interested in, let us know, because we're very interested in supporting extensions or whatever that we need to enable users to take advantage of that. As I said, we have some demos down on the show floor, so by all means come and take a look at them. Microsoft has their variable rate shading demo as well. Make sure to ask them to show you the tier 1 one, because I noticed they went from off to tier 2 right away. But we support the tier 1, and you can definitely see you get a pretty good speed up here. And a lot of the demos, if you look closely, it's actually pretty difficult to actually tell the difference, because either the things that you're not directly looking at, they're on the periphery, they're motion blurred, whatever it may be. And this is something that actually, from a developer point of view, it's just a state, it's just a bit that you set, and then you get this 30% performance boost. So that's actually kind of a nice thing to have in the API, in the hardware these days. Okay. So then we'll just kind of wrap it up here. We've got this new Gen11 architecture, which Anton went into great detail with, which is great. I actually think that this is the first time Intel's gone into this much depth on our architecture, and I think you'll see more of that into the future. Our capabilities for a Gen11 mainstream device is this 1 teraflop, which we think is actually a pretty strong in the market. We've got these great new features. We've got the CPS variable rate shading tier 1 support. We've got the tile-based rendering support for your bandwidth limited applications, and anything else you want to add on that, Antoine?
No, I mean, we are pretty excited about it. We're really looking forward to see what you guys are going to make with it. And we are releasing the Gen11 white paper this week that goes into all of this into a lot more detail. So definitely go and check this out. And yeah, that's it. We'll open for questions.
Yeah. So if you have questions, please come up to the microphone and.
Just a quick one. You mentioned that you turn off your tile-based deferred rendering when GPA is running its per draw analysis. Right. Is that true of the D3D12s and Vulkan's timestamps as well? If you had those in your title, would it have to disable them?
It depends on which query mechanism that you're using. I believe we have solutions for certainly events, and if you're doing a timestamp within a render pass, then yes, we would probably turn it off in that scenario. If it's only like a timestamp, just at some location, it's easy for us to do just that in the last tile, right? If it makes sense. Yeah. But it may not always make the most sense if you don't know that the tile-based rendering is actually occurring.
Okay. All right.
Yeah. But no, that's a good question. Other questions or comments? Thank you.